Okay, guys. I wanted to make a quick video, or as quick as possible, but I wanted to make a video to describe what I'm doing with my in-person students um, for chapter 11 because a lot of this stuff you can read about it, but it's a lot of geometry, it's a lot of terms, and some of them are very clear and make a lot of sense, and others don't exactly seem to make sense for students because you're just looking at a flat picture. So I'm going to try and do my best, and I'm going to try to keep this short, but I'm doing a in person, or not in person, a manual writing setup here. So the way this works and with the recording device I'm using, I can't pause in between like switching papers and stuff. So you guys are going to have to bear with me. I'm going to try to keep this short, but I can only do so much with this setup. But um, because of the way that writing online works, I just thought it would be better if I did it in person or did it by hand like this instead of digitally. Okay, so 11.1 for my students in class, I actually gave them a glossary, which I will upload to Blackboard, that had all of the terms from chapter 11 and even some terms from chapter 12 that are just geometric figures and things that some of them things we've seen before and some not. And I had them kind of just analyze how those words and terms and figures are connected. Basically, they needed to make a map of all of the terms and show what connections they could find. And so for you guys, because you don't have the chance to do that in class, I'm just going to go through as many of the terms as possible. So like I have a slideshow open with all of the terms, and there are 32 slides. And normally there's something like 10. So this is going to be a lot. So I'm going to run through this very quickly. The undefined terms means the things that we have accepted in our society as the foundation of everything else, and that is the point, the line, and the plane. So nothing can exist without a point. And then if you add multiple points together in one dimension, then that creates a line. And then if you add multiple points in two dimensions, that makes a plane. So we have specific ways that we name points. We name them based on letters, okay, capital letters typically. And so a point, because it is one space in our universe, gets one letter. So you name it from a cat with a capital letter only. You do not use lowercase and you do not use numbers. Okay. A line can be named with a cursive lowercase, or it can be named based on the points that are on it. So BC. But we cannot name it just line B because I can't find my ruler, so I'm just using my stapler. Excuse me. This point, this line here is also line B if I only give it one point. So you have to use 2 points to define the line because you're in one dimension. You've moved more than 1 point around. And then a plane, I want you guys to note, I did not draw a plane the way that your textbook does because I wanted you to see that a plane actually comes when you have 3 points. Any 3 points that are not collinear create a specific plane. And that means that I move in one direction between 2 points, and between the third point, I can move in these directions here. And this line can basically extend all the way out here. This line can extend all the way out and basically create this surface, this paper, because that's where all the 3 points are at, and that will continue on forever. That's what a plane is, okay? So basically any flat surface you see, you can imagine the edges just continuing forever, and that is a plane. And they can be in any dimension and in any orientation. All right, so the next points that you want to look at are, I'm trying out points. Oh, planes are named using 3 points. So C, D, E, F, because you need at least 3 separate points to make a plane. Okay, you cannot name this plane DF because that could be the plane that's on the paper, and then it could also be, I have a little card here, give me just a second, the plane that is on this paper that goes through there. Okay, and I can tilt that paper too. It can be here, it can be here, it can be this direction. all of those are separate planes. So you need 3 points to say which specific one you're talking about. Okay, moving on. Let's see. So that's describing what. So I'm just clicking through my slideshow. All right. Now, once we have these things, we need to talk about some of the special characteristics. So, or in relationships. So for lines, we have that they have separate points and all that. There are 2 different types of points when you're talking about lines. You have collinear. Sorry, I have my camera set up on the middle of this paper, so my hand is kind of like off of it. So my handwriting is going to be kind of messy. And then you have non-collinear points. So these are points that are all on the same line. So if I'm just going to use this paper as my guide, that was supposed to be straight on that line there. So these are collinear. Non-collinear means that I have put another point over here that's not on it. Okay. Let's see. Your textbook likes to toss in some other stuff, things like talking about between, and I'm not going to go too in depth with that, and that's not something I'm going to worry about with you. So let's see, A, B, C, and D. So I want to talk about this line. I can name it several different ways. I can name it AB and do a line basically above it. BA, BC, and CB. Notice that I'm kind of lazy about the way I do my lines, so I just put a half arrow above each one. It indicates the same thing. Or I could do AC and CA. All of those are acceptable. Okay, but let's say I wanted to talk about line segments. So this does not continue on forever, like indicated with this line here. This stops at these 2 endpoints, right here and right here. So let's call this D, and this is E. So segment DE would be indicated with a segment above it that does not have arrows at the ends because it does not continue on. Okay? And I can again write that as ED as well. But let's say that this does continue on in one direction forever. So here is FG. So this is ED. I can call this FG. And this is something a lot of students will ask me about. So I have a closed point above F, but G, it goes past G. So I need to have an arrow on that side to indicate that this is what we call a ray. It's like half of a line, but not exactly, because you can't have half of something that never ends. Anyway, and so some students will end up putting an end point above G and do the arrow the same way and put an arrow here. But if you do that, then you're saying that it starts at G and it goes through F and on forever. That's totally different. So don't do that. If you really wanted to put G first, you would have to put the arrow this way. That's not standard. We don't really do that. So just watch out for that kind of thing. So just like collinear, so again, I'm just running through the slideshow. Just like collinear, we have coplanar. It's the exact same idea. So I have this plane here that is connected by these 3 points. Let's call this X, Y, and Z. Those are capitals. And I include another point. How can I indicate this? It's too long. So let's say I put this pen right here. Yes, there we go. So I have this pen here, and I put a point right there. I don't know if you guys can see. There's a little, I just did a little scribble on this silicone thing here. So that's fine. I can put this point right here. So if you'll notice, this point is definitely not flat on the paper. That point is not coplanar with the plane of x, y, and z. So if we called that point, I don't know, J, we could say that J is not coplanar with x, y, and z. Okay? Let's move on. So something else that's kind of difficult for students to understand is skew lines. Everybody understands, whoops, that's messy, sorry. Everybody seems to understand the idea of parallel and perpendicular lines, of course, but skew lines are not parallel, they're not perpendicular, and they don't intersect, okay? And they're not even coplanar. So I'm going to draw a line here, and then I'm going to show you, let's see, let me move my camera a little bit. So this is a line that will go on forever flat on the paper. And this is a totally separate line. It's not touching the paper. It will touch eventually. I can even touch it right here at the end point. But this line will never somehow curve and hit this line right here. So these two lines would be a really great example of skew lines. I've never been able to show this using a drawing the way your textbook tries to do. So just be aware of that. It is something that can seem, I don't know, tricky just because it's a hard 3D image to depict. So your textbook likes to give, let's see, this line here with this segment here, and then they'll do another segment here that is kind of hidden by some 3D point they like to show. Goes through here and all the way up. And then they say that this is going down because that's supposed to be a 3D figure. And it makes sense, but it's hard to see if you don't have that visual spatial understanding of it. So just be aware of that. All right, a term that I have to specifically show to my students when I give them that packet of geometric terms is concurrent. And it's exactly what it it's exactly what it sounds like in that it happens at the same time. Okay, so if this is a point, let's just say that's point J again, and this is point W. They're in the same spot. They are concurrent. The same thing can work with lines. So there's line. Let's call that line M. That's supposed to be a cursive lowercase. And here is line, oops, I went kind of crooked, but you can see it. Here is line H. Those two lines are concurrent with each other because they exist in the same exact spot. They're basically the same line, just different names. A reminder, so we're going to move off of the notebook real quick. So sorry, I have like a cable for the recording right there in front of my pen too. So parallel lines. This is really hard for me to draw, so I'm just going to use the lines on the paper. So here is a line, and here is a line. And we actually have an indication symbol for parallel lines, and that is an arrow drawn on each one to show that those two are parallel with each other. So let's say I drew in another parallel line over here. I would do the same arrow, so that way I can show that all three of them are together. Let's say I had, let's see, down, over to down here. This line is parallel with this line. And you can just kind of trust that because I'm the one saying it. But if you are interested in how I knew to draw two parallel slant lines like that, send me an email. I can talk to you about it. It's a pretty quick topic. Or you can refresh with your college algebra stuff. Should have been mentioned then. So I want to show that these are parallel to each other, but not parallel to my original line. So let's call this line A, line B, line C, line D, and line E. So I know that line A is, let's see, parallel. Is that the symbol we used to parallel? No, it doesn't have the arrows. So line A is parallel to line B and to line C. I'm going to look that up because I don't think I'm writing that properly. So I'm going to put a little star next to it. And then I know that line D is parallel to line E, but A is not parallel to D. So you do a little slash through that. It's a lot of lines, but you're just showing that you're using symbols to show these things. And similarly, we have symbols for perpendicular. So I have this line here. We'll call that line H again. And then I have a line right here, which again, you can trust that those are actually perpendicular to each other. They're just a little wavy. That's just my drawing. Okay. Let's call this line N. And I can show that these are perpendicular to each other, kind of like the little arrows over here. I use a little box. That's to indicate that they are perpendicular and therefore they actually have a 90-degree angle here. Okay. And if I wanted to write down that they were perpendicular lines, I would write H and then I do a vertical with a horizontal that is perpendicular. H is perpendicular to N. That's how you would write that out. So, oh yeah, and this is correct. It looked funny to me because my handwriting's not that great because of the box in front of me. So there are some axioms and theorems in this chapter. An axiom is almost as strong as a theorem in that it is an understood statement and agreed upon, but a theorem is something that's guaranteed as true. It's been proven mathematically, and the proof is agreed. Well, I mean, is accepted by everyone. There's no holes in the proof in the argument. So let me write that out real quick. An axiom, and I'm not going to quiz you on that. I just want you guys to know. Hopefully you guys are in this to actually, learn stuff as well as get the grade. So an axiom is accepted, understood, and necessary statement. And a theorem is a statement that has been mathematically proven. I'll let you guys get that that should be an E there, sorry. That's messy. Okay. There are some axioms and theorems. There are a lot. I'm not going to mention all of them, mostly because I'm already almost at 20 minutes. So, got to be careful with that. Let's see. Just like how lines can be parallel, planes can actually be parallel. I'm saying this while you guys might need to pause the video and get these down. I'm going to change the page in just a second. Give you like 3 seconds to get that down. Alright, I'm going to change the page now. So bear with me. Like I said, I can't pause the video or else it's two separate videos and I cannot put those together. Not unless I use some pretty fancy editing software, which I don't have with me right now. Okay, so we're just on the next page. So, like I said, lines can be parallel. Planes can actually be parallel as well. Parallel planes. How am I going to draw this? I'll just do kind of what your textbook does. So there's one plane, and I'm going to, I don't know if you can really see it, but I'm going to actually do a little highlight in here to shade and show that that is a plane. A separate, that's like a flat surface there. Highlighter's not very visible. And then down here, I have another, let's see. Oops, that one's crooked, sorry. That's actually what that should look like. So those are two separate planes. Let me get another highlighter here. And those are parallel to each other. They hold basically the exact same characteristics as parallel lines. Never intersect, always equidistant from each other. You'll never hear about it except for this section. Okay. Intersecting planes are a little more interesting though. So we've got this plane here. And let's say I want to draw in an intersecting plane. So that may not look like it intersects yet, but this slanted plane is actually cutting through the flat plane. So there's the slanted one. Oops, sorry. So that's the flat plane cutting through. I don't know if that's super loud with the pens just dropping. I'm so sorry about that. I just realized that was happening. The flat plane is cutting through this plane here. And so they intersect at that red line. So when two planes intersect, they make a line. When a plane intersects a line though, so let's just draw in a line right here. We'll just say it goes in front of this one. When a plane intersects a line, it only hits it at one point. And that makes sense. Think about this surface as a plane, and this is the line. If it intersects, it makes one point where it actually hits. So this pen, if it were going through this paper as one line, no matter which angle it comes at, it still only intersects at one point, unless it's flat on the paper, which that just means that the line is on the plane. That's different. I'm still trying to hurry, guys. I'm about halfway through the slideshow. Let's see. All right, we got to move on to angles now. There's a lot to mention with angles, so I'm going to go fast. If at any point, I should have said this before, but if at any point I'm saying something that is too fast for you, definitely just pause the video, you know? Okay, so an angle, you probably already heard this before. Here's a ray. And to make an angle, it's at least intersecting with another ray. And so we have the side here, the side here. This point we call the vertex. Okay. I'm going to shade the interior of the angle. But that is not something that we really define so often. Let's put some points on it so we can talk about naming our angle. So here's A, B, and C. All right, so there are different names for this, and there's a symbol that you'd include. So kind of like the line above the letters. To make an angle mark, you just do this. Because my handwriting can get kind of scribbly when I'm writing, I actually put a little arc through it. Your textbook does not, because your textbook is neater than I am, of course. So bear with that. Hang on a second, guys. Is my light making too much of a shadow? I hope you guys can see. Oh no, I moved my light. Now it's okay. It's fine. All right. I lost my place. Oh, okay. So you can call this angle ABC, angle B, or angle C, oh no, angle CBA. But if I call this, so this is angle ABC, angle B, so it's centered around B, that's the vertex, or angle CBA, that works. But if I write down angle CAB, I am not talking about the same thing. Angle CAB is talking about CAB. That's what this one is. And let's say I wrote down angle, let's see, let's do one more. Let's do angle BCA. Trying to get another highlighter out for you. That's not coming close. Okay, this is good. So angle BCA is talking about that one right there. It's totally different. The same interior for part of it, but then notice how this is the interior of that angle that will continue on. So the interior of the angle that we drew out is this right here. The interior of angle ACB or BCA, it continues on this way. So it's totally different. It's not going to give you the same answer. What the key here is that you want to have the vertex as the middle letter or the only letter. So that middle point is the vertex. So in this case, A is the vertex of the highlighted blue angle. Okay, watch out for that. That's a common mistake when we first start this kind of thing. All right. All right, another term that comes up that students really, they miss this term all the time. Just, they're not paying attention to what it actually is saying. So, is adjacent angles. And in fact, adjacent can work for anything, not just angles. So I have, oh, my pen just dragged on the paper. I apologize for that. It's right here and then right there. So A, B, C, and D. So I have actually I have three angles here. I have angle ADB, angle BDC, and then I even have angle ADC. And I'll let you, in your spare time while you pause this, while you're watching, I'll let you kind of trace those out and see which angles I'm talking about. I'll give you 3 seconds to pause and do that, and then you can check with what I'm about to I'm going to highlight them. So I'll give you a second. Okay, so angle ADB, it's right here. And then angle BDC is right here. And then angle ADC is right here. That might look a little confusing when you're looking at all 3 colors just there, but they are, if you follow along with the tracing that I did as I read it, that's how I still read angles. I still have to say, okay, let me start with the first letter and then move my finger or move my eye along the angle to see where it's actually talking about, especially when you get to bigger pictures, which if you've been working in my math lab, you've already seen them. So angle ADB and angle BDC, when I traced those out, hopefully you noticed that I actually had a section that I traced for both angles, that guy right there. Because those 2 angles share a side, so angles that share a side, those are adjacent angles. So these 2 right here are adjacent to each other. It's and they don't overlap either. That's a big part of it. As they're next to each other, they just barely touch one side, and that's it. you guys can look up degrees, minutes, and seconds. And the example that you're given, it's got a little picture of a schoolhouse in it. If that gives you trouble, please let me know. But I see that I'm already getting up to 30 minutes here, and I still got about 12 slides to go. So bear with me. All right, acute, right, and obtuse angles are the different categories that we discuss. And basically, I don't have a protractor in front of me, but if you look at a protractor, I feel like this is the one good thing about me having a digital recording. When I do those, I can like pop images on the screen, but a protractor looks somewhat like this. It's a half moon, and it usually has a bit cut out of it. And there's like a point here, and it starts at 0 and goes to 180. And then some good protractors will actually start at 0 on this side as well and go to 180 over here. They're see-through, so you can see the angles all the way through. Here's 90. So please bear with the very ugly little drawing that I did, because it is important that we talk about acute and obtuse in these measures. But I am going to then show you how we count angles. Just it's the mathematical standard universally, well, worldwide, because we don't know how people do it in other parts of the universe if they actually existed. Anyway, that's just a little joke, guys. I can tell you're not laughing. I'm sorry. Anyway, so an acute angle is in this range right there. Okay? It's anything that measures less than 90 degrees. So it stops right up to there. And please note that I'm putting like an open point there to say that it goes all the way up to 90, but it does not include 90. Okay? So it's less than 90 degrees. And then a right angle is very specific. That is, again, I'm so sorry. I just keep throwing my pens down right next to my microphone. I hope that's not terrible for you. A right angle goes up to 90 degrees, and that's it. They're very specific, and they are how we use right angles to define whether or not something is structurally sound, and that is why it's a special angle for us. And then obtuse angles are anything greater than 90 degrees in this range, okay? So it's from 90, I'm sorry, not 90, it's anything that is greater than 90 all the way up to 180 degrees. And this is just when we're talking about the 0 to 180 degree scale, okay? Now, notice that I put 0 and 180 for both of these, and then I talked about acute going from left to right, because that's how we usually count. But actually, mathematically, we have all accepted that our angle measures start counting here. We go from 0 there, and that's when we're talking about like on a plane. When you start talking about stuff like trig functions with tangent, sine, cosine, you count like this. So 0, 90 to 180 to 270, and then all the way up to 360. You start right there when you count, okay? That might have been a little too much detail. Let's see, I've already got obtuse. Oh, we didn't talk about straight angles. So a straight angle is exactly 190 degrees. Let me include that. So very much like the 90. So it's here. It's exactly 180 degrees. Because, oh, it goes from 0 to 180. So there's 0 to 90 right there, and 0 to 180. So the vertex is here in the middle, but it makes a straight line. That's what we call a straight angle. It's 180 degrees exactly. Give you a second to get that down. Yeah. Okay, let me turn my page and then we'll move the camera back up to it. Oops, sorry, I knocked it over again. Okay, so we're going to talk about circles and arcs. And this is going to be terrible because, again, I am drawing by hand. Let me try doing, just get my eyeglass cleaner here. Ugh. Oh, why did I move it? Why did I move it? Sorry, guys. This is what it's like being in my class. For anybody who has not had me in person, most of you. I actually have one student this semester in one of my in-person classes. Okay. Oh, that is terrible. I tried to make it a nice circle for you guys. I'm sorry. Oh, man, that's really bad. Yeah, I'm going to have to redo that. I'll just do a rough sketch, and you guys are just going to have to bear with me. That's better than me trying to trace it out. Ugh, that's a shame. And it's not even good. Okay, so that's the circle. The very first thing that you need to note is that a circle is not everything inside of this space. A circle is actually all the points that I've just drawn here that are equally distant from this center, okay? So this is the center. Actually, I should have done that in red. I apologize, because then that can show you that it's like a vocabulary word. I like to color code my notes still. I think it's very helpful. So if I wanted to make a circle and I did not have a protractor, which I don't have mine here, it's in my office at work, I would actually have a very simple way of doing it. You pin the end of a piece of rope or string to one spot, and then you tie your pencil to the other end, and you just drag the pencil along against the string, because what that does is that makes all of the points that are the same distance from that center. Okay, and that length of the string that you have there, that is what we call our radius. I see that my hand is making a huge shadow. Sorry about that. Again, something that you'd have to deal with if you were in my in-person class. Okay, so in any circle, I have, any set of radii that I want to draw out. When I talk about those endpoints that they make, that creates what we call an arc. This guy right there, that is one arc. Now, in fact, that arc is less than half of the circle, so we can call that a minor arc because it's less than half of the circle. The other one that I have here, where's my green marker? That one is what we call a major arc. Oh, I shouldn't be doing that in marker, sorry. Let me erase that real quick. Oh, that's wrong side. Okay. That is my major arc. Okay. And then let's actually talk about how we name those. So this center, we'll call this center M. So this is actually circle M. That's not a symbol you'll see very often, though. People will just write out circle. But that tells us that the center is point M. Let's call this N Here is J. I don't like to use the point O because that looks too confusing to me. So I want to talk about arc NJ. I would write that down by writing NJ, and above it, very much like the lines, I'm going to do a curved line segment. Because that's basically all an arc is a curved line segment. Then I can talk about my radius. My radius is, one of them is NM, and I do a segment because it's just a segment. And then let's add in another point to talk about the major arc. So notice that I put NJ. That looks confusing because NJ is this arc and NJ is this arc. So I can talk about it. If I add another point, I definitely want to be specific and I want to include that point. At least this is how I do it. Your textbook may not do this because it just varies from book to book and teacher to teacher. Let's see, because this isn't exactly accepted. Like there's somewhat of a standard, but it can vary. So you could write my major arc. Sorry, I'm trying to write while looking at the screen, so I'm not like craning my neck around this box that's holding the camera. NKJ to really show which arc you're talking about. We're getting there, guys. We're almost done. Okay, and then let's talk about a segment that I have not drawn in yet. I'm going to draw it in using a different color. Oh, that's not bad. Okay, so the segment that I've just drawn in, I can actually draw in another one. Both of those are what we call chords, with an H after the C. So a chord, we could say NJ, and you still just do a segment because there's not any special way of writing that down. And we can say chord JK. Okay, and then let's say I extended this segment JM. Let's see, JKL. So this is point L right here. I have another chord then. And a chord goes from, let's say, segment from, or with endpoints. I know that this is really messy, guys, all of these notes. I'm just kind of throwing things all over the paper. I was really hoping for this to be shorter. So segment with endpoints on the circle. Okay, so I can't talk about NM as a chord. It's not a chord. That's a radius. Let's see. So I have JL is another chord. But that one actually goes through the center. So it's a special chord. It's a diameter. And just like how we can have more than one radius, we have NM, we have JM, and we even have ML. It's another one. Our diameters, we can have more than one. It's just I only have one drawn out, and that is JL. So a diameter is always a chord because a chord just means that it has those endpoints, and every diameter has those endpoints. Otherwise, it doesn't go. It's not a diameter. So there are some properties about the circle that I'm going to. Do I really need to go into those with you guys? I'm not going to go through all of that stuff. I'll do the circle properties real quick. Okay. So let's do a different circle though, since that's getting kind of crowded. Again, not bad. Unlike my usual drawings. So let's do a diameter here, a circle here, I'm sorry, a radius there, and let's do one more diameter. And let's name these. And F is for the center. So this is circle F. So we got a lot of little chords. I'm sorry, a couple chords. We have of several radii. We have several minor arcs and several major arcs too. I'm not going to go through all of them. If you guys want, you can pause it, you can write them all out, and then send me an email with a picture of everything that you've written out and say, is this correct? And I'll let you know. That's a good little check for you. I guess we could talk about semicircles. So there's semicircles. This is not an accepted symbol, but I'm just showing you what I'm talking about when I say the term semicircle. So semicircle B, oh no, not B, semicircle F would be, let's say, let me just use the highlighter so it doesn't mess up the picture too much. And I can erase it when I'm done, actually. Semicircle F. It's just half the circle, that's all. I don't know why your textbook makes a big deal about it. Erase that and get it out of there. Oh no, it stained the paper. Yeah, well, that's better than nothing. Okay, so let's talk about the central angle here. Okay, so this is the center. We are very concerned with the relationship between an arc, any arc, minor or major, and its central angle. So this angle right here. That relationship is actually very special, and it does have some connection to mathematical relationships. So let's I shouldn't have given you this picture. You know what, we can do this. Yeah, we can use this. Let me just draw in a chord between A and C. And then let me draw in a chord between, let's see, actually, let's draw in another point. It's going to go through F, point G, okay? And then so I'm going to draw in a chord D, G. And we want to find, so the question is, find the measure of arc AC. So example problem. I haven't done any problems with you guys because 11.1 is just tons of vocab. So find the measure of arc AC. Okay, I'm going to put equals question mark so that we know that's what the question is. And we know that AC has a relationship, it's associated with central angle, so we're just going to put angle AFC. And I haven't given you any measures yet, so bear with me. So the first measure you're going to get is, let's do this in a different color. 30 degrees here. Oh, my pen is my pen skipping? It is skipping. Give me a second. So 30 degrees here. I'm sorry if you hear squeaking in the background. That is my dog in the distance. Sorry about that. And then 60 here. That should be enough, actually. So we haven't talked about any angle measures or anything like that, except the straight angle. And I told you that that is 180 degrees. So if I have a straight line here and part of this is 60, then that means that this other part needs to help add up to 180 degrees. So I can find that actually really easily because angle GFC is what we're going to focus on. That is our straight angle because it's a straight line. Okay, so that means that it equals 180 degrees. And so we need to use that, because if we know that we have 180 total and here's 60, we're trying to find this, all we have to do is subtract. So if you do 180 minus 60, that will get you x. So that means that central angle is 120 degrees. Oh, that should be an x there. And that connection that the central angle and the arc have, so on a circle, if this is the center and we call the central angle x, then that means that the measure of the arc equals x as well. The measure, I should have written measure. So that means that the measure of arc AC equals 120 degrees. And that might seem funny to measure an arc in degrees, but that goes into some theory and some content that we really aren't going to get into. Okay, now this is the end of the slideshow that I really want to go with you. If you have any questions about the rest of this from 11.1, please let me know. I don't want to make you watch a 3-hour video to go through all the sections that we're going to cover, so I will make separate videos for the other ones. But I didn't want you guys to get this content without some instruction from me, because just seeing my notes from in class is not going to be enough, because I didn't even take notes for 11.1. So hopefully this helped. If you have questions, pause the video at any, go back to that part of the video, pause it, take a note, write out what your question is, and let me know. I am more than happy to go over with you. Okay, I'll see you guys in 11.2.